right. So that was Z80 or Z80, however you call it in your dialect of English. And so thank you very much indeed. And we go to the other microprocessor, the 6502. And so our next speaker will be Alex Dumont. And he will talk about his force called Alexforth. And it's for the 6502. So Alex, are you prepared to show your presentation?
Can you hear me okay?
Yeah, we can hear you.
Okay, let's share my screen now. Okay, that's not what I wanted to share. Okay, can you see the screen?
Yeah, we see the screen. And
okay,
yeah,
try to remove.
Great.
This.
Please go ahead. Thank you.
Okay. Okay, so thank you. I'm Alex Dumont. I'm going to talk about how I implementing my own version of Forth on my 6502 breadboard computer. So this is more or less the overview of the presentation. First, I will give a small introduction of my motivation, some background, and I will present an overall of the 6502 breadboard computer I have built. Then I will give some 6502 basics, so we can understand for those of you who don't know the 6502 what this processor was and the constraints of this processor. Then I will try to give an understanding of how I implemented Forth on this computer, and then finally a quick demo. I'm afraid I may have too much content, so maybe I will have to skip some part at some point, but anyway. So so to start, my motivation in this project is really to learn new things and enjoy. There is absolutely no professional ambition for this project, no financial or nothing related to money. So it's just to learn. And I discovered Forth in April this year, so it's really recent to me. And also I never wrote any assembly before this project really. So I'm sure if and I'm not a software engineer or a computer science engineer, so bear with me if you see horrible things to your standards, because I'm really a beginner in the field. So here is my breadboard computer. For those of you who may know Ben Eater on YouTube, he made a series about building a 6502 breadboard computer. So that's what I follow to build this computer. And you may recognize all the components of the same architecture. I just added some component at the top. So basically the computer has a 65CO2S processor, which is the most modern version of the late 6502. This one is a CMOS version and a static one, which means that you can pause, you can slow down the clock, or you can even pause it and it will still retain the register value. Then the computer has a 16 kilobyte of SRAM and 32 kilobyte of ROM. And there's also a 6522 versatile interface adapter, which will give a 8-bit general purpose I/O ports on the bottom, and at the top there is a ACIA, which is a asynchronous communication interface adapter. So basically, it's a serial port. That's how I will communicate with the computer using an FTDI USB dongle. As you can see, there is no keyboard nor any VGA display, but there is a 20x4 LCD display at the bottom. At the time, I also built an EEPROM programmer, but right now it doesn't work anymore, so I'm using a commercial programmer. So basically, doing the computer was fun, but I needed to put some software on it. At the beginning, I started with some simple 6502 assembly program, some simple register manipulation up to writing hello world on the LCD display. Then I developed some ROM monitor to be able to interact with the computer. And more or less, that's the time when I discovered the fourth language in March and April of this year. So I thought, okay, let's try to implement Forth. So for that, I read some book. I think the same book that Adrian mentioned in his presentation, the threaded interpretative languages. And also I read some article by Brad Rodriguez, which is in the core today. I think it was called Moving Forth. And also I followed a series of video on YouTube. It was called Bitwise, and there are, I think, 4 to 5 chapters about building a Forth on a RISC-V architecture. But I was inspired a lot by this series. So yeah, I will give you some 6502 basics for those of you who don't know the 6502. The 6502 processor is an 8-bit CPU, so it has nothing to do with a 64-bit CPU like the RISC-V. It's much more limited. And there's a 16-bit wide address bus, so it can address 64K of memory space, which will include the ROM, RAM, and I/O devices if we have. And except the program counter, which is not really a general purpose register. This one is 16-bit, all the other registers are 8-bit. So there is the accumulator, which is basically the only register that you can use. And then there's the X and Y indexes. So they are used, as we will see, in a specific addressing mode. And then there is the stack pointer, which is used to address the hardware stack of the processor. That's not what I will use for the data stack of Forth. Okay, so the hardware stack, it resides in memory page 1, so its address is from 0100 to 01FF, and there are specific instructions to push and pop values to and from the stack, this hardware stack. In my implementation, I will use the hardware stack as the return stack for Forth. Okay, so the 6502 has I think it was a dozen or maybe 16 addressing modes. So I'm not going to cover all of them, but there are 2 of them that I use in my implementation. And this one is called zero page index with X or Y. You can use both. So remember, X is a index register. In that case, for example, load A B0, that is an address in 0 page, comma X, it will mean load the content of address 00B0 plus X into A. So how does it work? Well, the base address is B0 in that case, B0. As we're in a 0 page addressing mode, it means that the real address is 00B0. The processor is going to add the content of X, which is 2. So it will take the content of B2 and put it into register A. So that's one of the addressing mode that I will be using in my implementation, and especially as we will see later, I use it to address the data stack of Forth. And okay, this one is a bit more complex. It's a 0 page indirect index with Y. So what happens here? In that case, it's the example is load A, parentheses B2, comma Y. So what the 6502 is going to do is read the byte at B2 and the byte at B3. So that's the consecutive one. And with that, it will build an address. In that case, that would be G100, and that's going to be the base address. And it's going to add the content of register Y, the index, to that base address to form the address from which it's going to load A. So in that example, load A from with index with Y from B2, it's going to load 9C into A. So it's this one. I hope the chart is self-explaining. I use where do I use this? It's in the the routing for the next routing in the inner interpreter. I will store at some address the next instruction pointer. So I will need this mode to be able to read the 2 bytes of the next instruction. So now entering my fourth implementation detail. So what did I need to implement a minimal fourth? I thought, well, at the beginning, I didn't really thought all these things because I went on the go, but retrospectively, I think these are all the things that I ended up doing. So I needed a minimum, very minimum set of words. So basically that's a starting dictionary, a core dictionary, a minimal program that started to run, some code to interpret that program. So basically that's the inner interpreter, and a data stack and return stack. And at this moment, having all this, I had some Forth running, but I needed to uncompile it in the code. That wasn't really interactive. So to be able to make it more interactive, I started to need some more complex code to build an auto interpreter, and having a way to look up words in the dictionary, and having also a way to compile new words. So right now I went to this step. I already have that, but at the beginning I didn't have that. Regarding design choices, my implementation is a direct threaded code, and the cells are 16 bits wide, so 2 bytes. This is what a word in the dictionary look like. So, well, I think it's quite standard. There is a header with a link to the previous word. Here, here it's the code for the word here in the dictionary. So the name is 5 bytes, 1 for the length and 4 for the letters. Then we can see a jump to enter. So this block is 3 bytes because it's 1 for the opcode for jump, and then the address of enter. Then all the rest is 2 bytes per word. So the data pointer, fetch, and exit. My implementation of the data stack, for the data stack, I'm using the 0 page. In the 0 page, at the top of the page 0, I have allocated 4 variables. So it's 4 16-bit variables, and below that, all the space is reserved for the stack. The 6502 make it very convenient to use the 0 page index with X. That makes it very easy for us to address the stack. So if we look at the beginning, for example, the stack could be or would be empty. So that would be this part of the drawing. Let's say X is F6, and if I want to put something in the stack, I will store something in address 0x. So that would be really 0 press F6, and 1x. So that would be a low byte and a high byte. If we look at this second example, there are 2 things on the stack. My stack grows downward, so the top of the stack is below the next one of the stack. Here, in that case, we have put 2 cells. So X is F2. If I want to put something in X, I will write it the same in 0x and 1x. If I want to read the top of the stack, I would read at position 2x, which is really F2 plus 2, which is F4, and 3x, which will give me the high byte, which will be 3 plus F2, so F5. That makes it very convenient to work with the stack. For example, if I want to drop something off the stack, it's simply, I need to simply increment X by 2. So it's 2 calls to enx, increment X. Sorry, I have no notion of how much time I'm taking, so I don't know if I I didn't put the chronometer. Sorry.
Alexandre, we are
Yes.
already in your slot, in your time slot. So try to reduce and go to the end.
Okay, so I will skip the interpreter because it's quite some content, and I think
If you
it's not
can
really
show
relevant.
it running,
Yeah,
it's
yeah,
fantastic.
I will show it running. Okay. So I will skip the development methodology, the features, what I have right now. Well, I have some defining words, some I have the hidden, reveal words. I can do recursive loops, and well, there are a lot of things that don't work right now. It doesn't adhere to any standard, only integer number, only hexadecimal representation, so no decimal. And okay, well, the demo. Okay, let's go to it. So I'm going to power the computer. I hope you can. I will try to do something. So, can you see this video here?
Yes.
Okay. Okay, I will try to have both things. So here you can see the computer. Unfortunately, the screen, the LCD screen, right now it's not showing anything. So just 2 lines are written, and the LED is on. Okay, so I'm going to enter it or just reset the computer. Okay, so it's showing the prompt. So that's it. So 1, 2 plus dot give 3. Okay, I can have a look at the words that are in the dictionary. So the format, I think, is not standard, but it tells us where is the header, where is the code field, and the word. Okay. And I will show you an example. So I'm going to exit the computer right now and send a small example. Instead of typing the example myself, I'm going to send it with the over the serial link. So it's going to be faster. So it's connected, and now it's sending the instructions. But basically, it's really like typing the words, just faster. So we've defined a constant port A, port DDR-A. So that's to address what I want to do here is blink the LED. So I've got a word that is off that's going to turn off the LED, on, turn on. T is going to switch the LED on or toggle it. So, okay, I'm going back to the computer. So right now, I think the LED is off. I'm going to turn it on. Can you see it?
Yes.
Okay, off. I can toggle it with T. And blink, I'm not sure if blink is going to show well on the video, maybe not. Okay. So that would be one example of the computer running. It's not much, I'm sorry. It doesn't do much calculation because it's also a very limited computer. So, and I've got another demo, which is demo.f. This one is going to write something on the LCD screen. It takes a little bit longer because it's going to send some words to interact with the LCD. What I should do later is define these as primitive, but right now it's not primitive, it's a secondary word. So I'm going to focus more on the LCD screen. Okay, I've left the code for the LED at the bottom. Okay, so maybe you can see it has written some things on the LCD. Okay, so well, that's it.
Fantastic. Excellent.
If you have any question, I'm open to questions.
Thank you very much.
Thank you for your time.
Yeah.
Well, I have just one question.
Sure.
I have just one question.
Yes.
What was it like to build that on a breadboard, and how long did it take?
Well, the thing of the breadboard, it's very fragile. So I'm really anxious every time I take it out of the box.
Hello.
Sorry. Yeah. So it's like a patience game to build it, really. you have to be really careful, but that's the only thing I know. I don't know how to do PCB right now, so I think the next step will be to build a PCB, but that will be another project maybe for next year.
That's really impressive. Really impressive.
Well, really, I just followed Ben Eater on YouTube, so it's basically the same computer. I have just added this chip at the bottom, but really the decoding logic and everything is the same. And I've just built the FORTH because
I love to see this kind of work. It's fantastic.
Right. Thank you.
It's actually still very impressive.
Yeah. Well, I'm impressed myself because having this working is
has a lot of power in this kind of developments. It was used in the past almost in every new single board computer as a testing implementation, and we have lost this chance today, and I love to see that.
Thanks.
Very fine project. I have this on my agenda as well, so I'm happy you did it.
And I also ported my own FORTH to another computer that was made recently. It's well, some other maker did a computer with 2 CPU. There is the Z80 and the 6502, and I ported my FORTH to his computer. It's called Cerberus 2080. Well, I don't have it right now to show you, unfortunately, but this one does have a keyboard interface and a VGA interface. So that was a challenge for me because I had to write some routines to interface with the screen and the keyboard and everything. And for example, when you arrive at the bottom of the screen, you have to scroll up everything. That was another interesting challenge, which I did in 6502 assembly, not in FORTH. Okay, well, that's it. Thank you.
Alexandre?
Yes?
This is Christian. Just curious, this hardware design, how close is it to the Apple II clones that we had in the 80s?
Well, unfortunately, I wouldn't know because
you were not there.
No, yeah, I was there because I was born in '75, which is, I think, the same year that the 6502 came out to the market. But I was too early, and my first computer actually was an Atari STE, so it was not. I didn't have any 6502 or Z80 when they were popular. So so I don't know. I don't know. I think it's. I don't know. It's the same processor somehow, but they were using, I think, the NMOS version, not the CMOS. And this one is probably using some more recent component like the SRAM, static RAM. I guess at that time they had a different kind of technologies. But other than that, this one is very.
Alexandre, when the Atari ST came out, FORTH was very popular. I used FORTH on the Atari ST, and many people, it was a good time for FORTH, 87, 88. After the 90s, FORTH popularity went down, but it was very popular in that time.
And I never heard of that, of FORTH at the time. When I had the Atari ST, I learned BASIC. I think it was called GFA Basic.
GFA, yeah.
Yeah, that's all I learned at the time. And then later in university, I learned Pascal and some C and that. I just really recently discovered FORTH this year.
And you need to know, and all the group, that the guys from GFORTH, these are German FIC, they started with Atari ST. Ben Peisand started with the Atari ST, and I tested on that time his software over the German Fortgesellschaft. I bought the diskette. It was only sold the media, and it was very beautiful FORTH. And he created, or he became from other developers. This was when Big Forth was born, the time of Big Forth for the Atari.
Yeah,
Okay.
this brings back lots of memory. In the 1980s, at the time, I just learned Forth, and I got a copy of the Fig Forth. I got all the copies of Fig Forth and brought them to Taiwan. And there I tried to teach people Forth, and we have a group in Taiwan. But in 1980, lots of pirates, the Taiwanese pirates, they tried to clone the Apple II. So I joined the effort with them and ported the Fig Forth 6502 to the Apple clones. So we got lots of fun with Apple II and with 6502 Forth on it. So that's when the Taiwanese Fig group started. Okay, so it lots of fun. But then all the pirates was banned from the United States, that they couldn't sell any Apple II in the United States, and finally they switched to cloning the PC, and PC doesn't have so much patent protection, and so the Taiwanese just we all go off the Apple II bandwagon and jump on the PC wagon. Yeah,
think the,
it's a good memory. Yeah, and then that you got a really beautiful computer there. You know, while writing that, it's not easy, but you got that beautiful board there. I really admire that.